Today, more examples about section 3.8. Take a review. Review number 1. Differentiation means compute a derivative. So, explicit differentiation means explicitly compute a derivative. Implicit differentiation means implicitly compute a derivative. Review number 2. Given an equation about x and y, where x is considered to be an independent variable and y depends on x. If we solve the given equation for y, then compute the derivative. This process is called an explicit differentiation. On the other hand, if we compute derivative by directly taking derivative on the given equation, then solve the resulting equation for y prime. This process is called an implicit differentiation. Now, example 1. Given this equation, part A, solve the equation explicitly for y, then differentiate to get y prime. This is the given equation. Now we solve the equation for y, move 1 over x to the right hand side, then we have this equation. Consider 1 as x over x. Then combine 1 and 1 over x. We have this equation. Now, 1 over y is x minus 1 over x. Therefore, y is x over x minus 1. After we get the function, now take derivative on the function. The function is a quotient, so we apply the quotient formula to compute the derivative. By the quotient formula, then derivative is equal to this. Derivative of x is 1. Derivative of x minus 1 is 1 minus 0. Simplify this expression, then we have this. This is the result of derivative of y. Part B. Find y prime by implicit differentiation. That is, don't solve the given equation for y, then compute y prime. Instead, take derivative on the given equation to get y prime. This is the given equation. Take derivative on the left side and on the right side. Then we have this equation. The derivative on the left side is a sum of two functions. 1 over x depends on x. It is a function of x. Y depends on x. So 1 over y depends on x. Therefore, 1 over y is a function of x. Now, by the summation formula, this derivative is equal to the sum of these two derivatives. About the second derivative, derivative on 1 over y with respect to x. We need to use the chain rule to compute it. Insert dy to the denominator and a dy to the numerator, then this derivative is equal to this derivative times this derivative. If we cancel dy, then this product goes back to this derivative. Now, we have 1, 2, and 3 derivatives to compute. Derivative on 1 over x with respect to x, we can apply the product formula to compute this derivative. The result is negative 1 over x squared. The detail is here. Derivative on 1 over y with respect to y, we can apply the quotient formula to compute this derivative, similar to here. But we can also use the power formula to compute this derivative. Write 1 over y as a power y to negative 1. Then by the formula for power function, derivative is equal to power negative 1 times y to power minus 1. So we get negative y to negative 2. This is negative 1 over y squared. So this derivative is negative 1 over y squared. dy dx is y prime. Derivative on the constant 1 is 0. Now, we solve this equation for y prime. Move the second term to the right-hand side, then we have this equation. Move y squared to the left side, then we have this equation. This is the result of y prime. Part C. Check that your solutions to part A and part B are consistent by substituting the expression for y into your solution in part B. In part A, we got that the derivative of y is this. And in part B, we got the derivative of y is this. Actually, these two results are the same result. From part A, we saw that y depends on x in this way. Y is equal to x over x minus 1. Now, plug in this expression in the y here. This is the derivative obtained from part B. Write y squared over x squared as y squared times 1 over x squared. Now, plug in the function in y. Then we have this equation. Apply this square to the numerator and to the denominator. Then we have this equation. Cancel x squared from the top and from the bottom. Then we have this equation. This is the derivative from part A. Therefore, derivative from part B is equal to derivative from part A. Example 2. Consider this equation. Part A, find y prime explicitly. Namely, solve the equation for y, then compute y prime. This equation is a polynomial equation in the y variable. The degree is 3. There is a formula to solve a polynomial equation of degree 3, but the formula is very complicated. As a result, solve this equation for y, then compute y prime. This solution process is very time consuming and also very tedious. So I decide to give up answering part A. Part B, find y prime implicitly, namely take derivative on the equation to get y prime. This is the given equation. Take derivative on the left side and on the right side, then we have this equation. Move the constant 6 outside the derivative, then this one is this. The derivative on the left side is a sum of two functions. By the summation formula, this derivative is equal to the sum of these two derivatives. Now, about this equation, we need to compute this and this and these three derivatives. To compute this derivative, the derivative of y to the third with respect to x, we need the chain rule. By the chain rule, this derivative is equal to the product of these two derivatives. To compute this derivative, we apply the product rule. Because the function is a product of two functions. X depends on x. It is a function. Y depends on x. It is also a function. So, by the product rule, then this derivative is equal to the derivative of the first function x times the second function. Second function is y plus first function times derivative of the second function. So we have this equation. Now, derivative of x to the third with respect to x is 3x squared by the power formula. Derivative of y to the third with respect to y is 3y squared by the power formula. dy dx is y prime. X derivative is 1. So we have this equation. Now, solve this equation for y prime. I first simplify the equation by dividing the both sides by the number 3. Then I have this equation. Distribute the number 2 to the two terms. Then I have this equation. Now, move x squared to the right side and 2xy prime, this term, to the left side. Then I have this equation. On the left side, factor out y prime. Then I have this equation. Move y squared minus 2x, this factor, to the right side. Then I have this equation. And this is the result to part B. Part C. Verify that the point lies on the graph of the given equation. To answer this question, plug in the point into the equation and see whether or not the equation holds. Now, plug in the point 3 into the given equation. Then the left-hand side is 54, and the right side is also 54. So left side is equal to the right side. Therefore, the point satisfies the given equation. And therefore, the point lies on the graph of the given equation. Part D. Find the tangent line to the curve at the point 3. That is, write down the equation of the tangent line to the curve at this point. I plot the graph of the given function on my computer. The graph looks like this curve. The point 3 is about here. At this point, there is a tangent line. To write down the equation of the tangent line, we need to know the slope of the tangent line. In part B, we have computed the derivative. Now, to get the slope of the tangent line at the point 3, we just need to plug in the point in the derivative. Then the slope is -1. Now, we have the slope and 1 point on the tangent line. By the point slope formula, the equation of the tangent line is this. Simplify this equation, then this is the answer to part D. Example 3, part A. Determine the points at which the curve of this equation has a vertical tangent line. Part B. Does the curve have any horizontal tangent lines? Explain. I use my computer to plot the graph of the equation. The graph looks like this curve. From this diagram, we can see that there are 2 points on the curve where tangent lines are vertical. We need to determine these 2 points in part A. To find a vertical tangent line, I compute the derivative because derivative is the slope of a tangent line. This is the given equation. Take derivative on the both sides of this equation, then I have this equation. Apply the summation and subtraction formulas to this derivative, then I have this equation. About the second derivative, the function is y to the third. It is a power function. So I want to use the formula for a power function to compute the derivative. But this formula requires all the variables are the same variable. Therefore, before I apply this formula, I use the chain rule to write this derivative as the product of these 2 derivatives. Now, I have 1, 2, 3, 4, and 5 derivatives to compute. Derivative of x with respect to x is 1. Derivative of y to the third with respect to y is 3y squared by the formula here. Derivative of y with respect to x is y prime. And this is y prime. This is 0. Derivative on constant 0. Now solve this equation for y prime. move the second and the third terms to the right-hand side, then I have this equation. Factor out y prime on the right side, then I have this equation. Now move 1 minus 3y squared, this factor, to the left side, then I have this equation. This is the result of y prime. A vertical tangent line has the slope positive or negative infinity. So to determine where a vertical tangent line is, I set the denominator here to 0. Then slope is 1 over 0. 1 over 0 is either positive or negative infinity. Then solve this equation. I have two numbers. These two numbers are the y coordinates of this and these points. To find the corresponding x coordinates, I plug in these two numbers back in the given equation. Then I get the x coordinates of these 2 points. Therefore, the answer to part A is at this point and this point, tangent lines are vertical. Part B, does the curve have any horizontal tangent lines? Explain. This is the slope of a tangent line. Because low value for y can make this quotient 0. The answer to part B is the curve has low horizontal tangent line. Example 4. Given this equation, find the second derivative on y. Namely, take derivative twice on y. This is the given equation. Take derivative on the both sides, then I have this equation. Apply the summation formula to this derivative. Then this derivative is this sum. About this derivative, I want to use this formula. But this formula requires all the variables are the same variable. So before I can use this formula, I apply the chain rule. Write this derivative as the product of these two derivatives. Now, derivative on x with respect to x is 1. Derivative of y with respect to x is y prime. Derivative of sine of y with respect to y. Now I can apply this formula. It is cosine of y. And this is y prime. Now solve the equation for y prime. Move the second term to the right-hand side. Then I have this equation. Factor out y prime. I have this equation. Move cosine of y minus 1 to the left side. Then I have this equation. This is the first derivative on y. Now, take derivative again. About this derivative, because the function is a quotient, I can apply the quotient formula to compute the derivative. By the quotient formula, the derivative is derivative on the top times the bottom minus the top times the derivative on the bottom. then all divided by the bottom square. Then about this derivative, I apply the difference formula, then I have this equation. About this derivative of cosine of y with respect to x, I need the chain rule to compute it. By the chain rule, I can write this derivative as the product of these two derivatives. If I cancel dy from the bottom and from the top, then this product goes back to this derivative. Now, derivative on 1 is 0. Derivative on cosine of y with respect to y is negative sine of y. And derivative on 1 is 0. Then I have this equation. 0 times cosine of y minus 1 is 0. Negative 1 times negative sine of y times y prime is positive sine of y prime. Simplify this expression a little bit, I have this equation. And rewrite this fraction as this fraction times y prime. I have this equation. About y prime, I have compute it above. Y prime is 1 over cosine of y minus 1. So plug in this in the y prime here. Then I have this equation. A fraction times a fraction. Numerator times numerator. It is sine of y. Denominator times denominator. It is cosine of y minus 1 to the third. This is the answer to the second derivative on y. About the computation of this derivative, I have a remark. When I compute this derivative, I apply the quotient rule to get this equation. When I compute this derivative, I apply the chain rule to get this equation. So in this computation, I use the quotient rule first, then the chain rule. Here is a second computation of this derivative. In this second computation, I use the chain rule first, then the quotient rule. By the chain rule, I insert dy to the bottom and a dy to the top. Then the derivative is the product of these two derivatives. If I cancel dy from the bottom and from the top, then the product goes back to this derivative. To compare this derivative, 1 over cosine of y minus 1 with respect to y. In this derivative, the y now is considered to be an independent variable. By the quotient formula, this derivative is derivative on the top times the bottom minus the top times the derivative on the bottom, then all divided by the bottom square. Derivative of 1 is 0. Derivative of cosine of y minus 1 with respect to y is negative sine of y minus 0. Then I have this equation. Now, simplify this expression. 0 times cosine of y minus 1 is 0. Negative sine of y is sine of y. So I have this equation. dy dx is y prime. So I have this equation. This result is the result here. Example 5. Given this equation, use implicit differentiation to find dy dx. This is the given equation. Take derivative on the both sides, then I have this equation. To compute this derivative, I first simplify the function. I let u below x times y. Then the function becomes e to u. Now, to compute this derivative, I apply the chain rule. By the chain rule, this derivative is the product of these two derivatives. If I cancel du, then the product goes back to this derivative. Derivative of e to u with respect to u is e to u. Now, remove u. Plug in x times y in u. Then I have this equation. To compute this derivative, I apply the product rule because the function is a product. X depends on x. It is a function. Y depends on x. Y is a function of x. By the product rule, this derivative is derivative on the first function times the second function plus the first function times derivative on the second function. Derivative of x with respect to x is 1. Derivative on y with respect to x is y prime. This is y prime. Now, solve this equation for y prime. Move this term. This term has y prime. I move it to the right side, then I have this equation. Now, factor out y prime, then I have this equation. Finally, move this factor to the left side, then I have this equation. This is the result of derivative on y. Let me finish section 3.8 with this question. About implicit differentiation and explicit differentiation, which one is more useful? The answer is implicit differentiation is more useful because in real applications, one usually cannot solve an equation for the y variable. In the case, an explicit differentiation doesn't work.